this is the third video of a Proof by Induction series for OCR Pure Core AS Further Maths. In this session we will look at using induction to prove results about divisibility. In this example we want to show that the expressions are divisible by 3 for all m greater or equal to 1 with m in the natural numbers or positive integers. Let's start by expanding and seeing what we come up with. Well, we're going to have 3m squared minus 9m minus 2m plus 6, and then we've still got a minus m. If we gather up those terms, we find that we have 3m squared minus 12m plus 6. And you can probably see that it's quite easy to take a factor of 3 out of that expression. So we end up with 3 lots of m squared minus 4m plus 2. This factor 3 implies that this must therefore be divisible by 3. So let's just write that up there. So factor of 3 implies that it is divisible by 3. In the second example, we're also trying to do the same thing. If we can show that there is a factor of 3, then automatically we've shown that the expression is divisible by 3. Well, you may remember that 3 squared equals 9. So we're going to use that fact and write that as 3 squared to the m plus 1 minus 3, which if we want to we can write as 3 to the 2m plus 2 minus 3. And then if we just take out a factor of 3 again, that just becomes 3 to the 2m plus 1 minus 1. And once again we have this factor 3 here, so that same assumption or the statement that if you've got a factor of 3 therefore it's divisible by 3 also holds for the second expression. In neither of these two examples did we need to use proof by induction. We were just looking at how we show that something is divisible by a particular number. However, it is not always as straightforward to pull out a factor, and therefore sometimes we do need to prove by induction, or indeed in a question we may be directed to do so. In the following example, it is not at all obvious where we might get a factor of 8 from. Let us just remind ourselves quickly of the 3 steps for mathematical proof by induction. If you need to read these through, please pause now. Going back to our example, to prove by induction that 7 to the 2n minus 1 plus 3 to the 2n is divisible by 8, we will start with step 1 and check the n equals 1 case. So, for n equals 1, we would have 7 to the 2 times 1 minus 1 plus 3 to the 2 times 1, which in this case equals 7 to the 1 plus 3 squared, which would equal 7 plus 9 equals 16, which equals 2 times 8. Therefore, as there is a factor of 8, for the case where n equals 1, the expression is divisible by 8. Moving on to step 2, we will assume it is true for n equals k. So in other words, 7 to the 2k minus 1 plus 3 to the 2k is divisible by 8. So let's call it 8p, where we're choosing p to be some other factor. Maybe it's an expression, maybe it's another integer or natural number. probably be an expression, but this is how we make this assumption that for n equals k, that the expression is divisible by 8. Just as we have done in previous mathematical proof by induction, we will now go on within step 2 to consider n equals k plus 1. As we did in the previous video, it is really worthwhile trying to write down somewhere what it is that we're trying to work out. So, if we've got n equals k plus 1, we're trying to show that 7 to the 2 k plus 1 minus 1 plus 3 to the 2 k plus 1 equals 8 times some other expression. Alright, so we need to have a think about that and have that in mind, written on a piece of paper, but not within our proof. Continuing with step 2, this is what we have for n equals k plus 1, and we need to show it's divisible by 8, and we know that we can use this assumption about n equals k that we've made. So let's write this as 7 to the 2k plus 1, because we've got here the 2k, and then we'd have the plus 2 minus 1, and 3 to the, let's write it out as 2k plus 2. So we've just simplified that a little bit for n equals k. And then I know that I'm going to be trying to use this here. I really want to be able to use that assumption. Because if I can use that assumption, automatically I'm pulling out a factor of 8, which may really assist me here. So I'm going to take out 7 squared. So if I take out 7 squared, then I'm going to achieve this 7 to the 2k minus 1 inside the bracket. And here I can take out 3 squared, knowing that then I've got a 3 to the 2k inside that bracket. So I'm starting to head towards being able to use my assumption. Luckily I know what 7 squared is, so I can write that as 49 lots of 7 to 2k minus 1, and I know what 3 squared is, so I can put that in there. And then I can say, well, actually I've got 49 of those and 9 of those. Let's just take 9 of them for the moment and say, alright, so I've got 9 of that expression there, and then I've also still got 40 of these left. So hopefully now you can see that that bracket there is the same as that one up there. So I'm now in a position to say, well, I've got 9 lots of 8p, and because I know that 40 is 8 times 5, I can say, well, actually I've got 8 lots of 5 times 7 to the 2k minus 1. Therefore, I can pull out a factor of 8, which is what I'm after all, and say, well, that's fine. I've still got, inside the bracket, I've got 9p plus 5 lots of 7 to the 2k minus 1. I'm not really that interested in some ways about what's in that bracket. What I'm really interested in is the fact that this factor of 8 implies divisibility. by 8 for the case where n equals k plus 1. So having finished step 2, we then go on and write out our concluding sentence for step 3, which is the same as the examples we did for the series patterns and also for the matrices. And I'm sure that if you want to read that through again, you can pause and do so. And that was the third in the 3 videos on proof by mathematical induction.